Okay, question 3 is mainly about runtime analysis, and we are given a nested array that is a m times n matrix, and know that m and n there are both large. Okay, so for the first given method red herring, there are three return statements. In the first part, that is the if conditional block, we check that if our array has no rows at all, or that in the first row we have less than 5 items, that we have at most like 4 items in total. But note that m and n are large, so we don't really have to consider like this case. Let's assume that we can always come back if that is not the case, but we can just kind of like ignore that first to simplify the entire problem. Okay, so let's focus on the nested for loop now. One glance at the nested for loop, it suggests that at any given row, if I have the fifth item, then I will return -1. Since we have a large m, we can kind of assume that we would always have the fifth item in our first row, and we will be able to return -1 in at most 4 steps. So this means that, assuming that m is large, we are kind of certain that we would have a fifth item at the first row. So we can bound it with tether, like tether 4 steps can be further simplified to like tether 1. So at the end, we can conclude that yes, red herring runs in a constant time on average. Okay, the second given method is Crimson Tuna. Again, we have 3 return statements, and the first case is that if my array, like if the matrix has at most 3 rows, then I would return 0, right? Yeah, 3 rows only, and I will return 0. Okay, note that the extraction of the length variable takes constant time. Okay, but then again, we know that m and n are large, so we can kind of like just like keep this aside first. Let's look into the nested for loop. We'll return -1 when we are at the start of the fifth row. And to get to the fifth row, if it exists with large n, we will need to travel through all of the previous 4 rows. Again, with large n, we are kind of certain that we will need to travel through 4 n items to get to the start of the fifth row. So with that certainty, we can bound this with tether and simplify it to like tether n. Like the other cases, for the other cases, we will return 1. So this is a tricky part that we might have to resolve if we just like directly not consider for like smaller values of n in our matrix. In this case, notice that we don't really consider what is the case that I only have 4 rows. Like if I only have 4 rows, I would pass through the if conditional block, but I would also pass through the entire nested for loop, right? Because I don't have a fifth row, so it will never enter into the if condition inside the nested for loop. And I will return 1 after I traveled through the first 3 rows. So getting to the start of the 4th row after traveling through the first 3 rows, this means that we will travel through 3 n items. With a large n assumption, given that certainty of large n, we are able to bound 3n with tether and simplify it to tether n. So at this point, we are able to conclude that yes, Crimson Tuna runs in linear time on average. Okay, the final method we have here is Scarlet Coin, and judging from the final return statement, um, which recursively calls Scarlet Coin on split portions of sorted array. This is a recursive method. So let's start from the base case. We have start and end index. If start equals to n, or n is just at one index next to start, we will check that whether the value at start is equal to x. If it is not, then we will get the middle index. You can verify on your own that this computational formula over here will get you the correct middle index. Just note that start minus n, it will be a negative value, meaning that we are getting the middle index backwards from the n index. Okay, so with the middle index, we again check that whether we have the value x. If that's not the case, then we split the entire sorted array into the left half and the right half. And at each split portion, we check for the if condition. Otherwise, we also get the middle index and check that if the middle index returns x value. If it doesn't return x value, then we further split it into left and right portions. Yeah, and it will go on and on. So in this case, the worst case, which is the condition that we can upper bound on, is that if split portion start does not equal to x, or that like split portion middle does not equal to x, then we will just keep splitting the split portions into half. Like eventually we will check for all items in the sorted array. This means that the upper bound expressed in big O terms would just be like O of the length of the sorted array, which is omega n as given in the problem itself. Okay, note that the algorithm here greatly resembles binary search. However, in binary search, we narrow down the part of the sorted array to recursively call the function on. Like for example, if you know that x is smaller than start, then I would just recursively call scarlet coin on the left portion. Otherwise, like if x is larger than the value at index n, then I will recursively call scarlet coin on the right portion. So in this case, since like scarlet coin recursively checks for like the existence of like x at start and middle of each of the split portions, that is not a binary search. Okay, so like just one thing to note. Okay, so for part B, why can we only give like a big O runtime but not a tether runtime? So we know that the rule is that if our function for a big omega, which denotes the lower bound function, equals to our big O function, that is the upper bound function, then we will have a tether function, like on average expression. In our case, let's think about the lower bound. Like for lower bound, that means that we are able to return true if the start index of our sorted array is equals to like x, or that the middle index of our sorted array is x2. So like in both of these cases, it would just take like constant time. However, like we get that our upper bound case is like big O n. Since they clearly don't equal to each other, so we don't have a tether expression in this case. Thank you.